5 part 1. Man, these videos are long. Anyway, different cultures have developed creative forms of games of chance. For example, Native Hawaiians play a game called Kanani, which uses markers and a board and is similar to checkers. Native Americans play a game called Topidi, in which toss sticks determine how many points a player receives. When designing a game of chance, attention must be given to make sure the game is fair. If the game is not fair, or if there's not a reasonable chance that someone can win, no one will play the game. In addition, if the game has prizes involved, care needs to be taken so that prizes will be distributed based on their availability. In other words, if you only want to give away one grand prize, you just make sure the game is not set up so 10 people win the grand prize. So take a spin. Consider the following game. After you spin the wheel at the right, you win the amount spun. Explore using blah blah. That's just a spinner that sometimes it lands on 0, sometimes it lands on 4. So if you play the game 10 times, how much would you expect to win? What if you played 30 times, 100 times? Explain your process. Well, so here's the thought with this, and this is where it gets really kind of weird. Expected value isn't what a lot of kids think, and some kids take to this and it's super obvious and some kids don't. But if I played this game twice, I would expect to win $0. I would expect to win $0 once, and I would expect to win $4 once. So if I played this game twice, I would expect to win a grand total of $4, which means I expect to win $2 every time I play this game, which makes 0 sense because I can never win $2, right? So expected value doesn't have to be a value that you can actually win. Expected value essentially says, what are the odds that I'm going to, how much do I expect to win every time I play it? So again, on average, I expect to win $2. I'll never win $2, but if I play twice, I'll win $4. 4 divided by 2 is 2. So kind of a weird idea. So if I play this game 10 times, I expect to win $20. If I play this game 30 times, I expect to win $60. If I play it 100 times, I expect to win $200 because I expect to win $2 every time I play the game. So if you're to play once, what would you expect to earn according to part A? And again, 20 divided by 10, 60 divided by 30, and 200 divided by 100 are all $2. And I could never win $2. So it's sort of weird. Is it actually possible to win $2? No, it's not. So again, kind of a weird deal there. So a couple of different ways that we can calculate. I didn't go too much into the ways of calculating, but this is one way. I win 0 once, I win 4 once, that's $4, and I would play twice, so that would be $2 each. Another way that you can write this out would be, you could say this. I would expect to win $0 half the time I played this game, and I would expect to win $4 half the time I played this game. And so that would be 0 times a half, plus 4 times a half is 2. I would expect to win $2. So you can see I get the same answer either way. So I'll probably solve the next one both ways as well. So it says, what if the spinner looks like the one at right instead? If you win the amount that comes up on each spin, how much would you expect to win after 4 spins? Well, if I played this thing 4 times, and this is where it gets a little bit interesting, okay, I would expect to win $4 1 out of every 4 times I played this thing. I would expect to win $100 1 out of every 4 times I played this thing. And I would expect to win $0 2 out of every 4 times I played this thing. Well, think about it. A quarter of 4 is 1. A quarter of 100 is 25. And half of 0 is 0. I would expect to win this thing $26 every time I played this game, right? Because every time I played this game, I would expect to win this once, this once, this once, and this once. We can actually cut this in half. So again, I would expect to win $4 once. I would expect to win $100 once. and I would expect to win $0 twice. Right? I broke that up. So now I'm winning $104, and I'm going to divide it by these 4 instances, which is $26. So it looks a little bit different. So I expect to win $26 after 1 spin. I expect to win $104 after 4 spins. So kind of interesting. So again, the expected value is $26. Even though it doesn't matter that I'll never spin at 26. The bottom line is I expect to win 26 on this. Excuse me 1 second. I got distracted. So anyways, Gustavo described his thinking for part B this way. Half the time I'll earn nothing. 1/4 of the time I'll win 4. 1/4 of the time I'll win 100. So this should look pretty familiar. It's roughly the same thing in a different order, right? So again, you can do it this way or this way. It doesn't matter. Either way, you get the same amount. So it says Jesse has created the spinner right. This time, if you land on a positive number, you win that amount of money. However, if you land on a negative number, you lose that amount of money. Want to try it? Explore using that. And sometimes it comes up positive, sometimes it comes up negative. I'm going to jump back real quick. How much do they charge you to pay this game if they're going to play this game if it's going to be fair? They should charge you $2 because you'll pay $2. Sometimes you'll lose 2. Sometimes you'll win 2, and it'll even out. This one, they should charge you $26 to play because half the time you'll lose the $26. A quarter of the time you'll lose $22, but the other quarter of the time you'll make $74 back. And in the end, it'll even out. So if you wanted to play this game and they charge you $1 to play, you should play this game all day long because even though you'll lose that $1 sometimes, it'll more than offset by the wins. If they play this game and they charge like $50 to play it, even though you could win more, you should not play this game for $50 because you're only expected to win $26. So you're beginning to get a look into how Vegas works. They might give you more than you put in, but more than likely they're going to take more than you put in, and that's how they build it. So if you look at this one, I love this question. Before analyzing the spinner, predict whether a person would win or lose money. So what do you think? Would you win or lose money? And often what I get kids saying is that you would make money because 6 is bigger than 5. Here you would win $6. Here you'd lose $5. 2 and 2 balance out. So they say you would be more likely to win money than you would to lose money. So let's see if that's true. It says now calculate the expected value. Well, a quarter of the time, and again, I don't know how we want to do this. I mean, I guess we could do something like this and break them into 8s. Right? And we could do that, although that looks kind of messy. And we could just say, all right, well, I would have 2 6s. I would have 3 -5s. I would have 1 -2. And I would have 2 2s. So hopefully you see what I'm saying on breaking it down that way. And if we did that, we could see our expected value. I would have 12. Minus 15 would be -3, -5, so I would have -1, and I would play this thing 8 times. So my expected value would be -1/8. So you would actually expect to lose money. Your expected value would be -1/8, which is kind of crazy because that's not what a lot of kids see when they look at this. So again, hopefully you see when you add this up, this is 12, 14, 16, so I have 16 positives there. But then I have 5, 10, 15, 17 negatives. So I have more than 1 negative and I have 8 spins. The other way that we could do it is we could say, 1/4 of the time you're going to get a 6. 1/4 of the time you're going to get a 2. Minus 3/8 of the time you're going to get a -5. And 1/8 of the time you're going to get a -2. Actually, I should be adding there because I have the negative here. So long story short, I get 6/4 plus 2/4 minus 15/8 minus 2/8. Again, I don't have a common denominator, so I'll make this 12/8 plus 4/8 minus 15/8 minus 2/8, and you'll see we get -1/8. So I don't care if you do it this way. I don't care if you do it this way. You could use a calculator and turn these into decimals as well. and you would have gotten minus 1/8 is 12.125. So you lose 12.5 cents every time you play this. So this is a great game, right? Here's why this is a great game, because it looks like you're going to win money, but you're actually losing 12.5 cents every time you play it. So it's kind of nice, right? You give the illusion that the person who's going to play it's going to win money, and yet they lose money, but slowly enough that they don't get suspicious. Every time they play it, that's another 12.5 cents in your pocket. So pretty kind of a crazy game. It says, what would the expected value be if it were fair? If it were fair, you would expect it to be 0. It would be just as likely to make money as you would to lose money. And how could you change the spinner to make it fair? Well, there's a couple things that you could do to make it fair. I mean, I don't know. You could make the spinner go like this and change that to a 6. So -6 and -2, right? So that it was even. You could do that. Or I think the easiest thing to do would just be to keep the spinner. And what you're going to do is you're going to pay somebody 12.5 cents to play this game. So they pay 12.5 cents to play the game, and then now everything will be even because that's the expected value. So kind of interesting what the expectations are there. I'll pause and set up the last part of the video. Question for part A. It says double spin is a new game. The player gets to spin the spinner twice, but only wins if you get the same amount both times. And this is going to be an 1/8. So obviously this will be 3/8 and then 2/8 and 2/8. And I'll probably set it up like that. It says use an area model or tree diagram to show the sample space. I'm going to set up an area model right now to answer this. So let me put it on pause. Made an area model of the winning ways. Like, I didn't care about the losing ways. Like, obviously here you get a 1 in 100, you lose. Here you get 100 in a 1 and you lose. And they're both just as likely to happen 3 out of every 64 times. But I do know that I can win 1, 5, 9, 18 ways out of 64, right? So that's how often I'm going to win here. So it says use an area model or tree diagram to show the sample space and probability of each outcome of 2 spins. Well, I made an executive decision that I wasn't going to calculate all the ways of losing because I don't care. I only care about the ways of winning. And I can just assume that, again, using the complement, remember the complement is the opposite. I know if I win 1, 5, 9, 18 out of 64 ways. So if I win 18 out of 64, there we go. So if I win 18 out of 64, well, then I must lose the complement of that. I must lose whatever 64 minus 18 is, which I believe is 46 out of 64. So I'm going to lose 46 out of 64 times I play this game. And I'm only going to focus on the 18 ways I win. All right, so it says, what's the expected value when playing this game if you can play the game for free? So I'm going to get 100. 1 out of 64 times. I'm going to get 10, 4 out of 64 times. I'm going to get 5, 4 out of 64 times. I'm going to get 1, 9 out of 64 times. And don't forget that I'm going to get 0, 46 out of 64 times. So if I figure that out, that's 100 out of 64, plus that's 40 out of 64. That's 20 out of 64. And by the way, you'll see why I like that common denominator. You didn't have to have a common denominators, but it's so easy for me to add this now. Plus 9 out of 64, plus 0 out of 64. I'm going to have 140, 169 out of 64. So I expect to win $169 every 64 times I play this, which means that I should win $2.64 about. That's about $2.64 every time I play this. So what's the expected value of this game if you play it for free? It's about $2.64. And if it costs $3 to play this game, should you expect to break even in the long run? No. You should expect to lose. You expect to lose 36 cents every time you play, right? And then it says, this is a fair game. I would say, and I'll answer this over here, no, not fair. If they don't charge, you're making $2.64. If they do charge $3, you're losing 36 cents. But to make it fair, they could just charge you, I don't remember exactly what it was, $2.64 0.0625 cents every time you played it, which is unlikely they'd ever charge that, but that's what would make it exactly fair. All right, that is part A.